what do we need to know about the linear correlation coefficient, other than that it's a lot of work to calculate by hand? First of all, the linear correlation coefficient is always between -1 and 1. In other words, -1 is less than or equal to r, which will always be less than or equal to 1. Now, if r equals 1, then there is a perfect positive linear correlation. In other words, the dots form a perfectly straight line. And remember, a positive correlation coefficient means the line is going uphill as you go from left to right. So let's add going uphill from left to right. Now, on the other hand, if r equals -1, then there is also a perfect linear correlation, but this time it's negative. So the dots form a perfectly straight line going downhill from left to right. And the closer r is to 1, the stronger the evidence of a positive linear correlation. That's what we saw and mentioned in the previous example, where r was 0.918 and our dots were in a pretty straight line. If the correlation r had been, say, 0.7, the dots would have bounced around more. They wouldn't have been in such a nice straight line. Similarly, the closer r is to -1, the stronger the evidence of a negative but still linear correlation. Now, the further you go towards the middle, away from 1 or -1, remember the r is always between 1 and -1, but the further you get towards the middle, so the further away you are from 1 or -1, which I described in the notes as being closer to 0, because of course that's right in the middle of 1 and -1. The closer r is to 0, the less evidence there is of a linear correlation. Now, there could be a correlation, just not a linear one. Remember, we said that this correlation coefficient r only tells us about how strong the linear correlation is. It doesn't say anything about the nonlinear correlation. So let's see some pictures of that. The first one is an example of a perfect positive linear correlation. The dots line up in a perfect straight line, and the r value is 1. On the other hand, if you look at the last one in the first row, the dots again line up in a perfect straight line, but they're going downhill. So this is a perfect negative linear correlation, and the r value is -1. Now, what does it look like if you start moving towards the r towards the middle? Well, if r is 0.9, so it's pretty close to 1, you have dots that are pretty much in a straight line, but they bounce around off the line some. If you look at an example with a smaller r value, so closer to 0, they still kind of linear. You can draw a line through them, a straight line through them, but they bounce around even more. Looking at the same kind of thing with negative linear correlation, if the correlation coefficient R is negative 0.9, the dots are pretty linear going downhill, but they bounce around some. Whereas if you look at an example where R is negative 0.4, again, they're not in such a nice straight line. You can draw a line through them, but they bounce around a lot. They're off the line quite a bit. Oh, and going downhill because the R is negative. Now, if R is really close to 0, that just means there's not a linear correlation. The second to the last picture, so second one from the right in the second row, that's an example of having no correlation. It doesn't look to me like there's any reasonable curve at all that you could draw through these dots. The last one, though, where R is also close to 0, there is a correlation there. You know, you could draw a curve through that. It looks like it would be probably some kind of quadratic, something with x squared, but it's not linear. So even though there is a correlation, a nonlinear one, the R is still close to 0 because, again, R doesn't measure at all correlation other than linear correlation. That's a good place to stop this lecture and this section. So I will stop here and see you in the next section. Good luck with the homework.